Hey everyone, happy Monday. Hope you all had a good weekend and are ready to roll this last week before we hit Christmas break. Today we're going to be looking at section 5.6. That's called Arithmetic Sequences, and that'll be on page 244. What we saw in lesson 5.5, so our last lesson, is that we looked at different graphs and we looked at a line or something on a graph, and we said, is it linear or is it not? So this would be something, a line that is linear. We also saw some lines that looked maybe something like this, and we said, nope, that is not linear because it does not have a constant slope, or it's not in a straight line. We also looked at tables. So we saw some tables, maybe that looked something like this, had 1, 2, 3, and the values were maybe 1, 3, and 5, and we saw, okay, these keep going up by 1, these keep going up by 2, so we know that we have a constant slope or a constant change up here in our x's, we have a constant change in our y's, so that is also linear. If we saw something, that's not it, there we go, nope, that's not it either, there we go. If we saw something where it went 1, 3, and then 12, well, then we would say, nope, we don't have a constant slope. We might have a constant change in our x's, but our y's, we go from a change of 2 to a change of 9, and that doesn't work. That would not make a straight line. Today, we're going to kind of build off the idea of being linear, or some function being linear, and we're going to relate it to something called a sequence. Now maybe we've seen sequences before, but all that a sequence is that it's a consistent pattern that numbers have. So I won't spoil it because I know you're like on the edge of your seat saying, okay, what is an arithmetic sequence? I can't spoil it all in the introduction, that would be lame. So we're just going to move on to the learning targets. Students will be able to extend, graph, and write equations for an arithmetic sequence. So we're going to have this pattern, these numbers that have a pattern, and we're going to be able to extend that pattern, we're going to be able to graph that pattern, and then write an equation for that pattern, which in a lot of ways we're already doing. Students will be able to solve real-life problems involving arithmetic sequences. So I'm going to show you some baseline and some basic problems that you'll see with arithmetic sequences, and then in your homework you'll extend the knowledge that you gain from watching this video to a real-life problem. So first we need to tackle some vocab before we can dive into it. The first word is a sequence, and I might have given this away a little bit, but a sequence is the formal definition. A sequence is an ordered list of numbers. So you can see with our list here, we have 5, 10, 15, 20, 25. That's a very familiar counting by fives. Every time we are adding 5. So there's an order. It's not just some random list. We're not just going 5, 7, 26, 47, 102. It's not just a random list of numbers. No, it's an ordered list. Now another term that we need to be familiar with, it's term. Each number in a sequence is called the term. So right here, 15 would be the third term in the sequence. 5 would be the first term, or first position, you could say as well. Another way to talk about the order or where in the sequence a number falls would be this more maybe mathy looking way, is a sub n. So if we're talking about a sub 3, we would be talking about the third term in the sequence. So we'd be talking about 15. If we were talking about a sub 1, we'd be talking about the first term, and etc. When they say a sub n, they just mean that some term in the sequence. It's just like the nth position, whatever term, it's nothing too specific. So here, the key idea, and built into that key idea, there are two more terms. One term that hopefully you could have guessed, arithmetic sequence. In an arithmetic sequence, the difference between consecutive terms is the same. So, like we've talked about in our last example, the difference between 5 and 10 is 5, 15, 5, 20, 5. It has a difference of 5. And if we were just going to keep going and keep going and keep going, it always would have a difference of 5, that common difference. Now, something to consider or something to notice is that we are always, they say that we're always adding in these, but really we mean we're always adding or subtracting. So we could have 20, 15, 10, 5, 0, -5. I should put commas between here. And the way that they talk about it, they would say that we're adding a -5 every time. But we could just think about it, that common difference is subtracting 5 would be another way. So in other words, this common difference, we can be adding or subtracting. But for now, we will not be multiplying or dividing. A good way to remember that for an arithmetic sequence that we are adding or subtracting is that it starts with, kind of sounds like arithmetic, which I guess arithmetic just deals with math in general. So maybe not just adding and subtracting. But when I see, oh, that's what it was. Hello. Total blank out. When we see the A in arithmetic, we need to think of addition. So that's how we remember that. That's how we remember that's adding and subtracting. Sorry, I kind of lost my mojo there for a second. But again, arithmetic sequence, it's just that common difference between each of those points or each of those numbers, and those can be either an adding difference or subtracting difference. So a question you might see, write the next 3 terms of the arithmetic sequence. First thing we need to do is we need to identify what is the common difference. So we look from -7 to -14. They added, subtracted 7. From -14 to 21, -21, subtract 7, subtract 7. So that's what happened in the first 4 terms of our sequence. So if we need to list the next 3, we can safely assume that we will subtract 7 from 28, subtract 7 from 35, and subtract 7 from 42. So our next 3 terms would just be -35, -42, and -49. Another question you might see dealing with these, graph the arithmetic sequence 4, 8, 12, 16, and kind of the rest of it there. And then it'll ask, what do we notice? So one thing that I need to point out, when we're dealing with these arithmetic sequences, if we were to put them on a table, the way we would put it on the table is that we would put the position up top, and then we would put the term on the bottom. So what I mean by position is that 4 is the first one in line. So its position would be 1, and the term is 4. Like we said, where's our definitions? Right here. The term, each number is called the term. So if we have our sequence right here, each number in it is a term. So the number that's in the first position is 4, second is 8, third is 12, and in the fourth position is 16. We could keep going, but we don't need to. So we put it in a table that lets us help identify our points. That our points on our graph are going to be 1, 4, 2, 8, 3, 12, 4, 16, and so on. We could go from there. So if we were to graph these, 1, 2, 3, 4, 2, 5, 6, 7, 8. And really all we need for a graph is 2 points. If we had a ruler, this might be a little straighter. Oops. And just from those 2 points, we can make our graph. So that's what it would be looking for in a graph. And it says, what do you notice? Well, we notice that this graph, in light of what we've been talking about, it's a linear function, or it makes a line. So what we just looked at is that these arithmetic sequences do form a line. And we know that we can write, lines in this form, y equals mx plus b. But leave it to math. When we are dealing with arithmetic sequences, we do not write things in this form. We write things, arithmetic sequences have their own form that they like their, their equation in. So this key idea, if you're following with me in the textbook, it'd be on the bottom of page 245. Let a sub n be the nth term. So a sub n is saying if we want to find any term in the sequence, you give me a term. It can be the 236th term, and we'll be able to find it. So let a sub n be the nth term of an arithmetic sequence with the first term a sub 1 and the common difference being d. The nth term is given by, so we find this 236th term by putting a sub 1. N just represents that 236, so 236 minus 1 times d, that will give us that 236th term. So I'm going to write this here so it's easy for us to see. A sub n equals a sub 1 plus n minus 1 times d. Now, that sounds complicated, but it's going to be super simple to see when we have this practice problem. Write an equation for the nth term of the arithmetic sequence, 14, 11, 8, 5, and so on. Find the 150th term. So first, when we write an equation, we still need a few things here. We need our a sub 1, so our first term, which is right here. So if we're filling this in, a sub n equals, this is just writing our equation, a sub 1, which is 14, plus, well, n, we don't know what term we want to find yet. We're just writing the equation, so n stays in there, n minus 1 times d, which, remember, is our common difference. So here we go. Minus 3, minus 3, minus 3. So then our common difference would be times a negative 3. So there's our equation right there. Now, when we do the second part, it says, then find a sub 50. So what that's saying is we want to find the 50th term. So we want to find out when whatever a sub 50 equals. Well, we follow our equation plus, remember, n is right here, is the term that we're looking for, and it's the 50th term, minus 1 times a negative 3. So if we're simplifying, we have 14 plus 49 times a negative 3. (14) minus 147. And if we follow it up here, we would get that a sub 50, so the 50th term, is negative 133. So this should not be a surprise to us, because if we are subtracting 3 every time, we'll see that we'll be in the negative pretty soon. I mean, if we subtract 3 again, we'll be at 2, negative 1, and we'll keep going closer or further and further into that negative space. So when we see that a sub 50 is negative 133, that should not be a huge shock to us. And as we're looking at this, you should hopefully see some similarities to what we've done with that linear function, with that y equals mx plus b form, and with this arithmetic sequence. That even though we don't have quite the same formula, but this constant change is a lot like our idea of slope. And this first term has a lot of similarities to our intercept. But we won't dig too much into all of that now, because it'll be easy to get that a little bit switched up. So if we look at our learning targets again, students will be able to extend, graph, and write equations for an arithmetic sequence. Now we extend the sequence by, where did it go? I did clear my ink. We extend the sequence by saying, okay, write the next 3 terms. And we said that this then went to negative 35, negative 42, and so on past there. That is how we extended the sequence. We graphed a sequence by making that comparison of saying, hey, we could put these in a table where the first term is 4, second term is 8, and go from there. And these are kind of like our x and y on a graph, and we can graph these. And then lastly, write that equation. Something that we need to be familiar with is this equation right here. That a sub n equals a sub 1 plus n minus 1 times d. That's an equation that we're going to want to have on hand. And a sub 1, remember, is our first term. N then is the term that we're looking for, our nth. That's the way we say it, nth term, which is given to us a lot of times. And then our d value is that common difference. Okay? Students will be able to solve real-life problems involving an arithmetic sequence. And that's something that you're going to do on the homework, where it might have something like, here's a real life, an example 4 from your book. Online bidding for a purse increases $5 for each bid after the $60 initial bid, and it gives you a table to kind of help you out. And then it wants you to write an equation based on that information and based on the table, which we just looked at doing. One thing I do want to add, sorry, you're like, oh, this video's done, probably about to hang up. Nope, got one more thing I want to add. One thing I do want to look at is when we are right here in this form, we could write this in a more familiar form. And when I have you write equations on homework problems, I would like it to be in this more familiar form. So what we really could do is we could distribute this negative 3 to each of these numbers. So it could be a sub n equals 14 plus negative 3 n plus 4. If we do a little bit of simplifying, 14 plus 4, if we put a negative 3 up front, 14 plus 4 is like this. Oh. Negative 3 times negative 1 just gives me positive 3. So that's 17. So this is a much more familiar form. So on homework and things like that, when we are writing these equations, if we're writing things in the best, most basic, or maybe not most basic, but the best form, what I'll be looking for is for it to be in this form right here. Notice, I mean, it's not y equals, but notice that this is our slope and this would be our y-intercept if we were to graph this. So that's one note to make sure to key in on when you're doing the homework and looking at those things. Other than that, now this is the last thing. So that is the last thing. Thank you again for hanging in there, for listening. If you have any questions, as always, shoot me an email and I can help you out. Otherwise,